Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 10th, 2026, just about 6 days ago. It demonstrates that tracking the class conditional entropy of a latent variable provides a reliable signal for detecting exactly when a diffusion model commits to a specific semantic class. The paper is titled The Entropic Signature of Class Speciation in Diffusion Models. And, as we'll see later, these findings effectively bridge statistical physics with practical model control, showing promising results on major models like Stable Diffusion 1.5. Figure 1 visualizes this entropy production. Panel A on the left uses a simple 1D model to show the mechanism. As the paths branch, the red entropy curve spikes, marking the exact moment of decision. Panel B on the right extends this to ImageNet classes. The graph shows that different objects emerge at different times. Notice how the blue tiger shark curve peaks at a higher noise level than the green paintbrush curve. The image rows below confirm this, as the shark's coarse shape resolves out of the noise on the right much earlier than the fine details required for the paintbrushes. Well, Figure 2 confirms these dynamics analytically using a high-dimensional Gaussian mixture model. Panel A plots the class conditional entropy for variance preserving, or VP, diffusion. Notice that as the data dimension grows, shown by the shifting colored lines, the transition point shifts, meaning commitment happens at different noise levels depending on complexity. Panel B contrasts this with variance exploding models, where the transition is significantly broader. Most importantly, Panel C demonstrates a universal scaling law. When the time axis is rescaled by the theoretical speciation time, all the VP curves collapse onto a single master curve, proving that the moment of class emergence is mathematically predictable. So, Figure 3 investigates how classifier-free guidance alters these dynamics on ImageNet. The top row tracks entropy under 3 strategies, while the bottom row quantifies the distortion relative to a baseline. In the left column, guidance optimized for FD Dino V2 shifts the entropy peak toward higher noise levels, visible as the green spike, which forces the model to commit to a class earlier. In contrast, the middle column shows that FID optimized guidance causes almost no entropic shift, suggesting it only refines details without changing the semantic decision. Finally, the right column reveals that constant guidance spreads this redistribution broadly across the timeline. Moving on to Figure 4, we see how this applies to text-to-image generation using Stable Diffusion 1.5. The graph on the left tracks entropy for different attributes added to a prompt about a wooden chair. Notice that global changes, like adding blue walls shown in the green curve, drop in entropy much earlier than localized objects like a cat. This indicates the model decides the overall style before figuring out specific details. The snapshots on the right confirm this. By stage B, the wall color is set, but the cat is still just a blurry patch. Alright, Table 1 provides quantitative backup for these guidance strategies on ImageNet. It compares optimizing for FID versus FD Dino V2 using limited interval guidance. Looking at the second column, we see the optimal noise ranges differ sharply. For FID, the best window is low, between 0.27 and 1.5, targeting later refinement. But for the semantic FD Dino V2 metric, the window shifts much higher, reaching up to 5.28. This proves semantic content is determined early in the high noise regime. To wrap things up, this work essentially gives us a temporal map for when meaning emerges in diffusion models. By tracking entropy, we can pinpoint exactly when a model commits to a concept, enabling more precise, time-localized control of the generation process. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.